So when I wrote yesterday the Navier-Stokes equations um, in this form, say dui dxi equal to 0 and dui dt uj dui dxj equals minus 1 by rho dp dxi. How many of you thought, what the heck is he writing? You would be very generous and you wouldn't say it like that. You might say, I don't understand what he's talking about. For how many of you was this? So, what's that? Oh, okay. Okay. So, only that side then. This side, everybody is okay, right? No? Okay, all right. So, let's see what this means. So, how many of you have had a course in ordinary differential equations? Does it mean others don't? How many of you haven't had a course in ODE, ordinary differential equations?
They might not have had a complete course, but they'll know.
You know about ODEs. Is there anyone who doesn't know about ODEs? What about PDEs, partial differential equations? You all know? Oh, that's way ahead of everything else. How many of you know about this notation, repeated index? Or how many of you don't know? Let's put it that way. Oh, okay. Not that many don't know. So basically what it means is whenever you repeat an index like this, you have to sum the thing over all possible values of the index. So if you're talking about 3 dimensions, this thing is a shorthand for du1, dx1, du2 or dx2, du3 or dx3 equal to 0. Okay, so just repeat, just substitute for I all possible values of the index, all possible values that I takes. So because of that, it doesn't matter if I wrote uj or uxj, because it's still a repeated index, so it is exactly the same thing. Okay, so this is a way of writing that the mass in the there is mass conservation that is obeyed by the fluid motion. And similarly, this thing here, this one here, is the momentum conservation for the ith component of the velocity of the flow. And you would have similar equations for, well, this is an equation for I in general, so you might write it as du1 dt plus all the other things. Similarly, you would write a du2 dt, etc. So this is really 3 equations here for 3 different values of I. So here J repeats itself, so it really is a shorthand for saying u1 dui dx1 plus u2 dui dx2 plus u3 dx3. Okay, you know this, you understand? And Laplace squared is so d squared. I can also write it as d squared dxj dxj ui. This will mean d squared ui or dx1 squared d squared ui or dx2 squared d squared ui dx3 squared, etc. Okay, so that's how it is. That's what it's supposed to mean. just a shorthand way of writing. You could use vectors instead of this notation, but that don't make it any easier in general. I don't know how many of you remember all the vector operations. But anyhow, therefore, this is mass conservation, and this is momentum conservation for the fluid. Now, this is what you want to solve for any given flow. With the right initial conditions, you have to say what the initial conditions are, and you have to say what the boundary conditions are. And this will tell you what kind of flow you're solving and with what you start. So that's the problem, mathematically or computationally, anyhow, that is the problem. So this here, uj or ui, I go back to ui just for the heck of it. Ui is the velocity in direction I, which is, I use I, j, k for, say, x1, x2, x3, or x, y, z. So I have a coordinate system like that, x1, x2, and x3, or this would be ith direction, or the x direction, as you might call it, j and y, and this is k and z. So you have a flow of some sort in this coordinate system, and you go here, a position which is x and t. This x, this dash underneath says it's a vector. So you have x1, x2, x3 in the three-dimensional coordinate system and at a given time, and you are solving for the velocity ui, ith component of the velocity using that. Of course, u2, u3 will follow. So you have to solve all of them at the same time. Okay. So that's the job. So I think, at least I hope you know what I have written down here. And if you could solve it as an initial value problem, for example, starting with some initial values of the velocity, you can just Taylor expand it and compute it for some time. But usually that is a very difficult process, and you cannot I mean, computationally you can do it, but analytically you cannot. But there are better ways of computing the flow than just doing expansions, and we'll talk about it later on. So now I want to see, mostly I want to tell you what the difficulties are in trying to understand the flow from these equations. So, if you take any flow for that matter, like the pipe flow we talked about yesterday, say a flow like this, and if you measure along this direction the velocity at any given instant of time, it may look something like that. It is, say, fluctuating flow in a turbulent flow. And if you measured it another instant of time, it may look little differently, and it may look yet again another different way if you measured it at a third instant of time. So at every instant of time, the flow is actually different, but you are not really interested in what's happening at every instant of time, but you want to know quite often, and it's not always the case, quite often you want to know what the mean velocity distribution is, for instance, or you want to know what the mean pressure drop is in the pipe. The pressure drop also fluctuates as a function of time. And so what does it mean to say you have a mean? It means that you sort of average these profiles taken at all points of time, and then you will get an average profile which is sort of like that. And superimpose that, you imagine you have these fluctuations. So that's the kind of philosophy that we will use in order to describe the flow and try to see how much of it we can compute. So the same thing I'm going to say, ui, which is the velocity at any spatial point and at any given time, is a mean value ui at x. And of course, it won't depend on time if you are doing the time averaging. Although time averaging is what I have in mind, it doesn't have to be that, but I will for now leave it like that. And then you have a fluctuation on it, ui prime, which will depend on x and t. Okay, so for now, for at least for this lecture, I'm going to use this notation that instantaneous thing that you measure is equal to sum of the mean, which is denoted by the capital letter, plus a fluctuation. Now you might, of course, write a pi at xt is again capital Pi x plus pi prime at xt. Okay. The density I am going to say is the same. It's not going to fluctuate. And I will also say that the viscosity will not fluctuate. It's a fixed number. So you have a given fluid, say air or water or whatever, at a given temperature and so on. Its velocity is the same. Its viscosity is the same and its density is the same. Now this is called in the jargon Reynolds averaging. After the first person who introduced it in the field, Reynolds, and it's mathematically something you can, of course, always write in this fashion, but you can always ask whether this is a meaningful thing to do. For example, if I had something like this, let's say as a function of time, I had a variable which was like this. So it was oscillating like that, let's say. Okay? And this could be, for instance, my ui. I'm not saying that it is, but it could be some quantity like that. And then you take the time average of this, that is to say, get the area under this whole curve, divide by the total time, and you will get a mean like that. Okay, this could be my capital ui, and the fluctuation around it would be my ui prime. If I have a quantity like this kind of division into a mean and a fluctuation is extremely useful, because I tell you a mean value, I tell you a lot about the function, right? I'm always telling you how much it is. It's pretty much mean plus a little fluctuation around it. So, for example, if I gave you that the average temperature in Singapore is 31 degrees Celsius, now that's pretty good, because every day it is the same, more or less. One day it is 32, one day it is 30, but it is more or less the same temperature. Now, if I tell you that the average temperature in Ottawa, the Canadian city, is 6 degrees Celsius, it may not tell you very much, because in winter it will go down to 20 degrees below zero, and summer it will go to 20 degrees. So if you were a traveler to Ottawa and I said, well, the average temperature is 6 degrees, you would just carry a nice sweater, light sweater, and it will kill you in winter. So it's not always useful, okay? This you have to remember that. While mathematically this is quite appropriate to do that, it's not always useful. It's worse if I have a quantity like this. As a function of time, if I had, let's say, some quantity, and that quantity was most of the time doing nothing, but suddenly it went off to some huge value, and like that, say hundreds of times the mean value, and the mean value will be here somewhere. Okay, because it occurs so sparsely, and the fluctuations could be very large. If I tell you the mean value of this is 1, whereas it sometimes could be 100 or 1000 or something like that, then it's not telling you all that much. Nevertheless, let's start with this idea, but keep that in mind. It's a very important idea to keep in mind. So if I do that, what will I'm going to substitute this back into this here, for example. Say what will happen to dui dxi. This is going to be dui dxi plus dui prime dxi, right? This is equal to 0. Now, I take the average of this thing. So let's say the average of that, and average of that, and average of that. And the averaging and differentials commute, so I just put that, and the average of this is this term itself, because it's already averaged. Average of an average is just the same term, right? And so this will go. Now you will have a thing like that, and this will be 0 because the average of the fluctuation is 0. So basically, I have then this term 0, so dui dxi equal to 0. That's the mean also satisfies the same equation. And you subtract the mean from the old equation, that's the sum of the two, you will also find dui prime or dxi equal to 0. That is, both the mean and the fluctuation satisfy the same equation, okay, separately. So not only does the full velocity satisfy this equation, but also the mean do. And my interest is really in getting an equation for the mean, because we just assume that the mean value or the average value is what matters, right? So the first thing what I can say is that the mean mass conservation equation is like that. Okay, is that okay? So what I have done is substituted for this sum here, and then average the whole thing, and I get this equation here. And if I wanted, I will subtract that average thing from here, and I will get one for the fluctuation as well, which I will use later on. Now, similarly, I will have here dui dt plus dui prime dt. And now this, of course, will be 0 because it's the d by dt of the average value. Average value doesn't change by our definition. So this will be 0. So I will simply get for this term dui prime dt. Now, and this is very easy again, 1 over rho d capital P dxi plus dp prime dxi, and if you average it, p prime vanishes, and I simply have d by dxi of capital P. And similarly that. But what about this here? This is the one that usually gives headaches, and that is the nonlinear term. As you can see, it's nonlinear because if I take it onto the inside, I will have something like ui uj. I mean, you'll have to do a little bit more than that. So this is an equation for ui. Everywhere you have the same thing, except here it suddenly becomes like a squared quantity, a product of two quantities. So while the degree of the equation is the same, it's nonlinear compared to the others. So now Let's take this here. So uj is, I write it as uj plus uj prime d uj plus uj prime or d, excuse me, I here, xj. Okay, now, and this is really equal to sum of two terms, dui dxj plus du prime or dxj. So a product of these two will give you four terms, and you will have uj dui dxj. Okay, that's the first one. And the next one will be, say, uj dui prime over dxj. So that's what I will have. And then I have here uj prime dui dxj. And then I have uj prime dui prime over dxj. Okay, so that's what I will have. And now you start averaging again. If you average, this thing is the same. This is an average, that's an average, so nothing is going to change. And here, average it, average of the product is the product of averages in this case. And so you sort of go, this is an average term, but this one has the average of a fluctuation. See, ui prime is a fluctuation, so that will vanish, and this will vanish similarly because this is so. But this will not vanish because a fluctuation and some other fluctuation here, for example, may have a very, very different kind of thing. For example, here I have a sine wave. Its average is 0, but sine squared, for instance, will give you this, right? So its average is not going to be 0. Its average will be something like that. So this will not go to 0, even if you average. So you have, therefore, so uj dui dxj. This is coming from here, which is this term here. Okay, uj dui dxj equals minus 1 over rho dp dxi plus nu nabla squared ui. And I will have this fluctuation term, which I can take on this side, and I can write it as d by dxj of ui prime uj prime average. So there is a little bit of step from going from here to here. What I have to do is I have to take it inside. If I take it inside, I'll have to subtract out another term, which would be ui prime duj prime dxj, and that turns out to be 0 from this equation. So, and then I average it, and that's what I have. Now maybe I should put a minus sign here, okay, because I've taken it onto the other side. So that's the equation for the mean. So since you cannot solve this equation for the velocity and pressure at any given instant of time in its full glory, what we have done is we have compromised by saying, well, we're interested only in the mean. And so how do we get the mean? We wrote it like that and put it back in here and did some manipulations, and we got this equation. Now, one thing you notice is that the mean velocity satisfies the same equation as the full thing does, but here the mean velocity satisfies an equation that is different from the standard Navier-Stokes equations. Even forgetting about this term here, I have a thing corresponding to this one there, and a thing corresponding to that on the first term on the right-hand side, and a thing corresponding to that on the second term there. And then I have this additional term which includes fluctuations and has only fluctuations in it. So the momentum balance for the mean quantities not only involves mean quantities but also fluctuations. So somehow this is the important thing to remember. So even if you are interested only in the mean values, you have no choice but to know something about the fluctuations, and that is this quantity that you want to know about. So one way to write this is if I write this as d by dxj of nu dui dxj. So that's a legitimate way of writing that. I put in nu inside only to make comparison here, although if it is fixed nu, then there is no advantage in putting it inside. So I have here d by dxj of ui prime uj prime average. So it's sort of like this term here. This is the viscous stress, and you have the term change of the viscous term, and similarly you might have here a stress term here due to the fluctuations, and its gradients like that. So if you think about this, what is happening is, what is this term here? So I have, let's say, a fluid parcel, and the momentum of the fluid parcel is lost by viscosity if you have a gradient in the flow. So it's the fluid parcel, you might imagine, rubs against neighboring fluid particles and loses momentum by friction, or gains momentum in some cases, for instance. Here, you have a very similar thing that is happening, and the momentum is lost or gained by fluctuations. So what this means is that, for example, in a flow like this, if I have a velocity of the fluctuation, which is ui prime there, and rho ui prime, let's say, is the momentum of a fluid parcel, and then you multiply this by uj prime, what it says is this fluid particle is moving to the neighboring layer, where in fact the momentum could be quite different. And in fact, you have therefore a momentum transport that is accomplished by this fluctuation term, the average value of that. And therefore, this is often in analogy to the fact that it's a viscous term, this is a viscous stress, and you might say this is like a turbulent stress. I think so far it is just a name and it doesn't mean anything. But sometimes people write in analogy to this, this one as say nu t d ui over dxj, for instance. So the idea is that when molecules move about and have collisions, they transfer momentum. In the same way, you can imagine, and this is not exactly true, but just imagine that there are turbulent eddies or parcels of turbulent motion that are moving about from one place to another and carrying with them momentum that they may release to the next position where they go to. So if it is true that this analogy can somehow be justified, you will be right in writing, just as you did for the viscous momentum transport by viscosity or molecular motion, a term like that, you would by analogy write something like that. But of course, this analogy has no real rigor to it, unlike here, but it is something people do pretty much all the time. And so I want to bring it to your attention that is the case. I will not dwell on it too much, but this is called the gradient transport model in general. It's a model for the turbulent transport. And this model might or might not work, and it works in some cases and it doesn't work in some cases. So in fact, the danger of something that works sometimes and not work some other times is you don't know when to use it and when not to use it. If you know it does not ever work, you can just throw it out. But if you know it works always, you can use it and try to find out why. But if it works sometimes and sometimes not, that's not a very good idea. So we have a reasonable idea of when it works and when it does not work, and but I can talk about it later on if you like. But for now, let's move on. So the point that I am making here is that even for the mean quantity, I have a term that involves fluctuations, and I have to know that somehow. So here, the true Navier-Stokes equations, we have four variables, as I already said yesterday, ui, that is u1, u2, u3, and the pressure, density, and viscosity are given already to you. And you have four equations. This is one equation, and one equation for I, one equation for J, and one equation for K. Okay? Or one equation for direction 1, 2, and 3. So I have enough number of equations for the variables. Now here what is happening is I have four variables, the velocities and pressure, so ui and p, and then I have this additional variable here, which is minus ui prime, uj prime, and I only have, therefore this is five variables, but I only have four equations, right? One equation and three here. So this, of course, makes the system indeterminate. You cannot have smaller number of equations than the unknowns. And that's a problem in turbulence. This is an illustration of the problem in turbulence, that you have more terms than the number of equations available to you. If somehow you could neglect it, then of course it's the same equation as that and everything would be fine. But you cannot. In principle and in practice, as I erased it too fast, if I wrote it like nu t dui dxj, and I compare the values of nu t and nu, this nu t over nu, this could be very large. It could be, I don't know, 100, let's say, put some number like that. In some areas in the flow, it is very close to unity, but in many others, it could be some large number. It's pretty large. And how large it is depends on the Reynolds number. So in principle and in practice, you cannot ignore this term at all. And this term, you can ignore or not ignore at your peril, and sometimes you will see that you can just ignore it, and sometimes you can't. So basically, you have to have this term additionally as well. So this problem is known as the problem of closure in turbulence. Closure problem. I mean, this is just a first step of the closure. I'll say what exactly closure is. The closure means simply that you don't have enough. A closure problem means you don't have enough equations for the unknowns that you have in the problem. Of course, you can write an equation for ua prime, uj prime, which I will do now. At least schematically, I will do it. But what happens is, because of this nonlinearity, I will have a term ui, uj, uk. If I write an equation for ui, uj, I'll get ui, uj, uk. And I write an equation for ui, uj, uk, I get a term ui, uj, uk, ul, something like that. And this goes on forever, and therefore at any given time or a given order, you are not closing the equations. So usually people go as far as writing an equation for ui prime, uj prime, and it is a very important equation, and so I'll write it down for you. I'll show you how to do it. But thereafter, people don't usually bother to write further equations, but start to say something about the unknown terms. Like here, I could have closed it by saying, well, this is d by dxj of, nu t dt dy dxj, and I sort of gave the number nu t. I put it 100, let's say. I don't know, just some number. Then I have closed the equation, right? Because everything is now in terms, there is no, this term does not exist as a separate thing because it's cast in terms of ui already. And so I have basically closed the equation. But as I said, this is not good enough closure because it's not always the case that something like this works. This is something you can measure. This is something you can measure. Sometimes nu t may go negative, sometimes positive, and sometimes small, sometimes large, etc. And even an average value depends on the flow. If you have pipe flow, it is one thing. If you have atmosphere, it is another. If you have something else, it is another. So you can't give a number. Unlike here, where for a given fluid, you always have the same number, where this one depends at least on the flow, and quite often on where in the flow you are, and very strongly dependent on it. And sometimes it could even go negative. And there are cases where that happens. So as a concept, it is already defective going from here to here. But in practice, also, it is very defective because you would have to compile a handbook of nu t for each given flow, each given position, and that's not how you might want to do it. So, in fact, we will try to get nu t for some flow later on. So now let's write, therefore, carry this on to the next stage of writing an equation for ui prime uj prime and seeing what kind of difficulties you have there. So I'll sort of schematically illustrate this. So I have here an equation for ui, and we wrote it as ui equals capital Ui plus ui prime, and I have an equation for capital Ui, and I subtract from here this equation, I get an equation for ui prime. Okay? I write it down for you, or at least some parts of it. And then, so let me say, I get an equation for ui prime over dt plus whatever uj prime d ui over dxj plus all the other terms that go with it. And I can just change the index from I to j. Remember, I'm interested in ui, uj prime kind of thing. So I have an equation which also has something like that. And now what you do is, if I want to write an equation for ui prime uj prime, I multiply this by uj prime, and I multiply this by ui prime, and I take this inside there, and I take this one also inside. I have to be careful how I do it and all that. And then I have, I can just add it up, add up the two things. You can do it in several different ways. But basically, I get an equation for ui uj prime, which I write down without doing anything. Ui prime uj prime average, well, that's my interest, right? Plus uj d by dxj ui prime uj prime average equals minus uj prime uk prime d capital Ui dxk minus ui prime uk prime. You don't have to write it down, but I want to illustrate some things here. dxk, and I have minus d by dxk of ui, uj, uk prime, uj prime, all of that, minus 1 by rho d by dxi of p prime uj prime, plus another term like that, which is d by dxi of p prime ui prime. And then I have 1 by rho of p prime here, dui prime or dxi plus duj or dui prime or dxj prime. So I have other things like that, okay? And then I have a viscous term, which is d squared ui uj prime or dxl dxl plus, or in this case, minus 2 nu. This is an important term, but I still write it very quickly and very short. dxl. It's not very important that you should write it down, but the main point is not only has the equation become more complex, it has many more terms that were simply unfamiliar to you, but also you have this quantity here, which is a third order quantity, which is coming from the same type of behavior. And also you have quantities that involve pressure and velocity, and pressure is a second order in velocity, if you think of it like that. So this, in some sense, belongs to the same class as this nonlinear term. And then I have the viscous term. So if I am thinking of this as a conserved quantity and I'm writing an equation for this, this is the rate of change in time, and this is the advection along streamlines, mean streamlines. And then I have here quantities that involve the fluctuations and the mean gradients in the flow. And I have these third order purely turbulent quantities involving pressure here, and velocity gradients, and pure viscous terms. So I have all this stuff. Now already at second order, it's very complex, and you can solve, if you say something about this and this and that, you can solve this for ui uj prime, put it back here, and you have got the whole solution. It's not conceptually, it's not a very hard thing. Now, it's a little complicated to interpret, but I would like to interpret each term for you. And so, what is useful for interpretational purposes is I contract this term. That is to say, I put I equal to j. What is I equal to j? ui prime. What does this mean? This means u1 prime or u1 squared, right? And for the second term, I have u2 prime squared plus u3 prime squared, and I put half there and put 2. This is the kinetic energy of the fluctuations, except for the fact that the rho is missing. As I say, rho is constant, so I simply assume that doesn't matter. So that's the kinetic energy of the fluctuations. So what I'm going to do is contract this equation, rewrite this equation by contracting the symbols, and you will see all of this will have some implications here. For example, here, dui dxl, doj dxl, all of these terms I have to put wherever there is I put j, and if it is a repeated thing, I sum over it. I have to be careful in what I do. But the point is that I would write an equation here, d by dt of q squared. So this stuff here this stuff here is q squared, okay? And when I say q squared by 2, that I put a half there and I put 2 here, etc. This q squared by 2 is the kinetic energy in general. So I write this symbolically. It's a little bit easier to write it like that. So uk d by dxk of q squared by 2 plus ui prime uk prime dui or dxk. Now, you see here, there are two indices, I and k. So you have to repeat them. So, and then each symbol becomes irrelevant, and I have just a scalar quantity. And this is equal to minus d by dxk of p by rho plus q squared by 2 uk prime, like that, plus mu I d squared over d xl dxl of q squared by 2 minus mu d ui prime or dxl dui prime or dxl. Okay, so I have this repeated index here, which means it is, excuse me, this simply means d squared over dx1 squared of this, d squared over dx2 squared of that, d squared over dx3 squared of that. And similarly here I have two repeated indices. This would be du1 dx1, du1 dx1, then I have to keep repeating these indices. So now it's sort of interesting to interpret this. I have a rate of change of kinetic energy of the fluctuations, and this is the time rate, and this is the change due to advection. And then I have a term here that involves the mean gradient and the fluctuation, product of fluctuations. And this is really interpreted as the production of energy. This is how the energy is being produced into fluctuations from the mean. So it's basically the mean gradient acting on the fluctuations that will increase the value of the fluctuations. And how does it do that? I mean, I'm interpreting it with some background in mind, but still I can tell you how it might happen. So let's say I have a vortex element in the flow, and there is a mean shear. That means this quantity is non-zero. Then what it will do is it stretch the vortex element in a certain direction, and it will change the energy, for instance. Okay, so a term like this is generally responsible for producing more turbulent energy, or turbulent kinetic energy. And so this term is the production term, and you can model it in some way if you are so inclined. And what this is a combination of pressure, and this is the kinetic energy here, but it is simply the transport of this pressure term, the pressure, by the fluctuating velocity. So it sort of has a combination of pressure and fluctuating velocity. And here is simply viscous transport here, and this is the viscous dissipation, because this is a negative, with this negative sign, it's a negative definite quantity. It's always losing energy. So yesterday I wrote, for example, dE or dt is P minus D with 1 over R and things like that. And you can see where that may have come from. So this would be dE by dt, and I'm sort of ignoring that, or I'm including that if I put it as dE over dt there. And this is the production term. I sort of ignored these, and I am justified in ignoring it if there is no real transport, or if I integrated the whole thing, for instance, if I have a boundary where the fluctuations are 0, or if the boundary is moved off to infinity or something like that, then these two terms will vanish, and I would have just the dissipation term, which is here. So that's how I wrote it down yesterday, schematically, without doing any of this kind of stuff. So this is the dissipation. And each of these terms has a different character. So you sort of, if you want to model it, that is to say you don't want to go on any further, but I want to modify it somehow. Let's look at the pressure term, what it will be like, how is it going to be interacting with the velocity. If you have, think of Bernoulli's equation where the pressure and kinetic energy are interchanged with each other. So if I have a large fluctuation in one direction, and that is contributing to pressure, then what it will do is the pressure fluctuation will go up, but then the velocity fluctuation has to go down. Okay? So the one that contributes to the increasing pressure fluctuations is the one that has the largest magnitude. On the other hand, when you think of pressure, which is a scalar quantity, becoming smaller instead of going up, then it is releasing the pressure into the fluctuations of velocity. It doesn't know which direction is preferred, so it releases the kinetic energy in all directions equally, more or less. So what it means is, it's taking pressure, it's taking the kinetic energy from the largest component, and then giving it to the others in some way, robbing the rich to feed the poor. So therefore, these terms have the feature that they take away energy from the largest component and give it to the others, as I said. And you can sort of write it in using that physics in mind in a certain fashion. And this one, of course, has to be modeled always as a positive definite term that will take away energy, and you will have to model it in some fashion. And so there are all kinds of ways in which you can model these different terms. So let me, yeah. Yeah. Let me just do that. Maybe it's better in the next one. I'll simplify this, and maybe we'll see it even better. Let's do that. So I'm now going to specialize this equation for interpretational purposes for a two-dimensional flow. Two-dimensional in the mean. So the mean velocity may be two-dimensional, but the fluctuations will always be three-dimensional. That is, you have, say, a flow between parallel plates, for example, one parallel plate like that, and the flow is going from my left to right in these pictures in between the plates. And it's two-dimensional in the sense nothing varies in this direction. Every variation occurs in this direction and in this direction. Okay? But in the mean it is always the case. So mean velocity is two-dimensional. But the fluctuations could be and would be, in fact, in all three directions and roughly equally. And I will want to tell you why it is so in a bit. So I have a situation where I have only u1, which is a function of x2, and u2 equal to 0, u3 equal to 0. And similarly, I will have things like d by dx2 of some any mean quantities will be 0, d by dx3. Sorry, this is true. So things like that. So I am considering such a flow, and I'm not going to write the whole thing down, but I want to interpret a few things for you. If I have only this kind of scenario, Then let's look at this term here. The only non-zero term will be for d by dt of u1 squared over 2 for that quantity, or maybe without a 2. That quantity, what I will have is 2 u1 prime u2 prime d u1 over dx2. I'm just concentrating on this term for now, and all the other terms will be there. Other terms meaning these other terms. Every other gradient of velocity is 0 because I can't have a u2, I can't have a u3 because u2 and u3 are set to 0, and I can't have d by dx3 because I've said it's two-dimensional. Now, if I write the equation for d by dt of u2 squared, this corresponding term will be 0. And similarly, d by dt of u3 squared, that will also be 0 because the gradients are not, there are no gradients in u2, u3, etc. Okay, so what this says is, if I have a two-dimensional flow, like a channel flow, a flow between parallel plates, the energy is being produced only in the first component, u1 squared. There is no production of energy in u2 and u3. You see what I'm saying? So I have a flow here, which is like that, and the mean velocity may be something like that. And the mean streamlines are always like that. And there is no variation in this direction at all. In principle, extending to infinity, I have direction 1, direction 2, and direction 3. And I'm writing an equation for the component of the energy, fluctuation energy in the direction 1 and 2 and 3 separately, that is splitting this into 1, 2, and 3, and I have these, okay? I have to go back here and put I equal to 1 and j equal to 1, and that's that equation. Specialized for this particular case. And then I find that the production term appears only in the direction 1 and not in directions 2 and 3. So energy is being constantly produced in direction 1, but not in directions 2 and 3. On the other hand, the dissipation term is there in all three directions. And in fact, they're roughly equal. This is something you couldn't tell from the equation, but I'm telling you that they're roughly equal. So what is happening is the energy is being constantly produced in 1, but it's taken out in all three directions. So this looks like a bit of an anomaly because if one component is always becoming richer and the other, all three are being depleted, the other two don't have anything produced constantly. So you might think everything collapses and I have fluctuations only in one direction, moving like that back and forth, and nothing happens. That, of course, is not true. So what must be happening is that what is being produced in one is being shared by the other somehow by some transport between 1 and 2 and 1 and 3. Right? And how is that done? That is done through these pressure terms, this thing here. And that's what I was trying to explain. So you will have here, the correspondence may not be exact because I may have factor 2 and things like that. So, but I write it down here for you, the pressure term. The pressure term in the first equation will be P prime d u1 prime over dx1. And I would have here d2 by rho P prime d u2 prime over dx2 prime, and 2 by rho P prime du3 over dx3 prime, du3 prime over dx3. Okay? So somehow these terms have to have an interchange of energy. Now notice one thing, and that is if I sum all of them up, it will be 0, because 2 by rho is all common, p prime is common. I have du prime, du1 prime over dx1 plus du2 prime over dx2 plus the du3 prime over dx3. And that by the continuity or the mass conservation equation, this equation here will be 0. See du1 prime over dx1 prime, du2 prime over dx3 prime. So what this says is, if you sum it all up, if I use u1 squared, u2 squared, u3 squared, etc., the contribution of the pressure terms is 0. That is, if you looked at all three of them, it means nothing. But they're sharing from here to these two. So this is always a negative quantity, and these two are positive quantities. So the pressure somehow distributes energy among three. So it's like this. Suppose you have 3 members in your family, and you're always exchange your bank balances. You give some to here. So outside, as your family, it doesn't change anything, right? You always have the same amount of money. But as an individual in the family, the money changes. And clearly, this has to happen because somebody is rich enough to give to the other two. So the wife makes more money and gives the kids and the husband, something like that. So now, how does this happen? I was giving you a qualitative understanding of how it may happen. It's like this. I have P, and I have U1, U2, U3. This is the quantities under consideration. And let's say I have in one instant, I have one velocity in one direction very much large compared to the 2 and 3 like that. This is fluctuating. Now, let's say this one goes down like this as a fluctuation, so the pressure gains because the kinetic energy is lost and the pressure increases. So I have a positive P prime when I have this is positive, and du1 dx1 is negative. So u1 is going down, P prime is gaining. So the product of these two will have one sign, which is a negative sign. And now, so what happened at the next instant is that they are all sort of like that, let's say. Now the pressure is large, and it is going down now. Pressure is coming down. And when the pressure goes down, the kinetic energy will have to increase to compensate for this. But the pressure doesn't always keep track of which component it gained energy from. It gives away kinetic energy to all three components more or less equally. So next instant, what may happen is, they might be like that. You see what I'm saying? So what was initially a very rich velocity component in this direction, or which energy in this direction, somehow by virtue of the pressure terms became roughly equal. I don't know if that's clear or not. I mean, that's as best as I can make it, but I can repeat it. So if you want, you can make it more quantitative in some other cases, but in general, that's the idea. And because of this, you can model it if you want to model it. The pressure velocity correlations, as they're called, pressure velocity gradient or pressure rate of strain correlations, etc. What it will be is its effectiveness is proportional to a difference in kinetic energy in different components. So let's say something like this, U2 squared or U3 squared. If this were 0, then there is nothing to transfer, right? Because they are all roughly equal and there is nothing to transfer. But if they are not 0, there is something to transfer by pressure terms. And the larger this quantity, that is, the larger the difference between one component and the two other components, the larger the magnitude of the pressure transfer. So the pressure transfer term, which is what I have there, is sort of written often as proportional to something like that. You can make it more sophisticated, but that's the general idea. Okay. So this business of taking this equation, or taking actually this equation, and modeling each of these terms in a certain way in order to solve for this, and then putting it back in and solving the whole thing so you can get the mean velocity, is known as Reynolds averaged Navier-Stokes equation modeling. So Rance modeling, as they would call it. Rance modeling means, so this is Reynolds average Navier-Stokes. So you have the Navier-Stokes, you have this. Reynolds averaged, because you put in the Reynolds averaging, and you get this. You can't solve at this level because of this. You go down or go up in one level and you wrote it down. And now here there are many terms, and each of them behaves differently. Each of them has a different physics associated with them, and each of them has to be understood in different ways. And so you model each term separately. Like I said, the pressure terms can be modeled like this, and other nonlinear terms can be modeled in different ways. And then you close it at this level. That is to say, anything that is unknown, you put it in terms of known quantities. That is the modeling part. So for example, the pressure velocity correlations had unknowns in them, but I just disappeared or made the unknowns disappear by putting them in terms of known variables, u1 squared, u2 squared, etc. And this is a very sophisticated process in turbulence practice now. So there are all kinds of industries, turbo machinery to atmospheric physics to boundary layer theory, internal flows, everything. People use the Rance modeling. So they have made it all very sophisticated. When I said proportional here, there is a constant of proportionality and things like that. You have to put it in the right tensorial form, satisfying all symmetries and all that. So they do that, and these numbers, unknown numbers sitting in front, are obtained by doing experiments in one flow or doing simulations in one flow and getting those numbers and imagining that those numbers will remain the same if you put it in some invariant form in all the other flows. So that's the spirit of Rance modeling. And if you want to be an engineer, for instance, using CFD, let's say, applicable to a whole class of practical problems, that's where you would go. You would more or less stop here. I mean, not exactly, but more or less stop here. Know how each of the terms are modeled, how the constants of proportionality are obtained, and work it out. We want to go a little bit further since we have nothing better to do. And so we will go forward and look at the lot of physics that relates to some simple cases. And that's where you generally learn a lot of analogies between physics, between fluid dynamics on the one hand, and let's say physics, proper physics, statistical physics, and so on the other. Okay, so that's, is this roughly clear, the situation? I mean, you may not have followed all the details, but the general philosophy must be very obvious. I'll repeat it for you again. So you have these equations that are known to you, are given to us by God himself or herself. And then usually, by the way, these Navier-Stokes equations are derived by it's a process in applied to Boltzmann equations. So people think that this is an approximate form of the Boltzmann equation. But actually, Navier-Stokes equations have a life of their own. That is to say, they may be derivable from Boltzmann equation using a certain process used in kinetic theory, but they have a separate existence of their own. That is to say, they don't have to depend on the Boltzmann equation for their validity. For example, in critical phenomena, when you go to very close to the critical point where everything will change very rapidly. All fluid properties change very rapidly. Anything like a kinetic theory or Boltzmann equation is not valid, but this one appears to be valid even there very nicely. And furthermore, Boltzmann equation is valid for, let's say, rarefied gases, but this, of course, is true for liquids, true for everything else that you can imagine, flows of that sort. So you have these equations. They are closed in the sense you have enough number of equations for the variables, but since you can't solve it exactly, if you can solve it exactly, what would you do? You would get the whole velocity here, and then if you want average values, you just average them, right, after you got the solution. But since you don't have the solution, you become clever by trying to write an equation for the average which you want by writing this in this fashion. And you get an equation for the averages. You have an unknown term here, and this unknown term can, of course, be written down with another equation like this, which also has higher order unknowns. And this process goes ad infinitum, and that is the turbulence closure problem. Okay, you do always have more terms than you have the equations. And somehow you decide to say, well, the returns are not going to be much better if I go to fourth order and so on and so forth. I stop right here. I stop right here and model each of these terms in some reasonable way that is consistent with the physical understanding of the problem. And then I solve this equation with all the models in it, get this ui uj, put it back here in, and solve that, and I have the mean velocity, mean whatever I want. Okay, that's the story. But let's go a little bit further, and I want to tell you all the beautiful physics that there might be in the problem. And to do that, I want to take a simpler flow that, like Picasso's thing that I showed you yesterday. You want to say something that is still recognizable, but it's not exactly rich with all the details. And as long as you remember that some of the physics that we explore there is not necessarily valid for every other flow in the universe, we will try to explain when it is valid and when it is not. As long as we are aware of that, there is nothing wrong with what we are going to do. But those who think that what we are going to do now is the entire story in turbulence will be wrong, because we will in fact ignore a lot of things, and you will see what that lot of things are. So suppose I had a flow in which there were no gradients whatever. No gradients means, well, this will vanish, and d by dxk of this quantity, d by dx1, d by dx2 of these averages, that will also vanish, because everything is homogeneous. Everything is the same everywhere statistically. And so I will simply have a kind of rate of change, probably with some advection, and of course dissipation always happening. So you will not have production, you will not have all this pressure, velocity, and things like that. We will later on show they will exist, but they will vanish for this case. So I want to talk about a case of homogeneous turbulence, and you will immediately see why it is sort of special. So I have a case where, let's say I have a turbulent flow somehow in somewhere there. If I made any statistical measurements here and here or here anywhere, they would all be the same. So the translational invariance of single point statistics. Not only single point statistics, for example, if I took one velocity there and another velocity there, and I computed their average, time average. So I took velocity there and velocity there. One instant they are like that, another instant they may be another thing, etc. I take the product and take the average of the product. That average product will be the same as long as the configuration of this is the same. That is, I translate this configuration anywhere in the flow, the product of the two averages will be the same. You understand what I'm saying? So if I took a next order product, so let's say a triangle like that, got the velocity here, here, and there, and computed their average, time average, if I translated it to another position, as long as I keep the same geometry, that will be the same. So that is one what's that? I didn't say that yet, but that's another constraint you can add. That is, in fact, it's rotationally symmetric, or it's isotropic, you might say, and that's even more specialized. This is just homogeneous for now, but if, as he says, it were isotropic, not only would these products remain the same if you simply translated, but if you rotated them, they would also be the same. So I'll get to that particular specialization later on, but for now, let's say it's homogeneous. So that's the problem, and so you want to know whether such a thing ever exists, a homogeneous flow, and so I'll spend a few minutes trying to say such a thing exists, at least you can create them, and sometimes what exists is close enough approximation to this in some cases. One example, although I know of no one who has made this experiment, I made a reference to that yesterday very briefly, is if you had a box, a big box, and you sort of, the box was all closed, temperature same on all sides, and you just shook the box a little bit, keep shaking like that. Then, except for very close to the walls, where everything is going to be zero by boundary conditions, in the majority of the box, the fluctuations will be the same everywhere. I mean, same statistically. So that's the kind of thing you have to keep in mind. Experimentally, how one realizes something like that is, for example, let's say I have a tube like that, and let's say I put a propeller of some sort there, another propeller here, and I spun the propeller slowly. After a while, what happens is the fluctuations that are created by the propeller will fill the rest of the thing, and away from the propellers for a certain distance, you might have this kind of rough homogeneity. Another way you might do that, and this of course has been done, another way you can do that is same tube. So what I now have is a grid here. I'll tell you what a grid is. Another grid, let's say like that. And now what is a grid? It's looking into it, it will be like that, a grid of bars, let's say like that. Better constructed than my drawing, but it's the general idea. So I have one grid there and one grid there, and I sort of oscillate them a little bit, back and forth here. And again, this central part eventually gets filled by fluctuations, and these fluctuations are basically homogeneous, roughly. Another way to do that, which is a little bit more tricky to understand, and you might understand that this might be so. Intuitively, you might say, yeah, okay, it's clearly something is happening here, something is happening there, but far away from there, it's really not dependent on how it was generated. A third way, which is very standard practice, is use the wind tunnels and wind tunnels with grids. Um, a grid is, as I said, exactly what I had. I'm doing it a little better this time, like that, say that way. And now imagine I have a flow like this into the grid. So for those of you who have not seen a wind tunnel, that's how it will look like. And I have flow coming in here, and I put a grid there. There's a lot of stuff in here which tries to make the flow smooth and nice and all that. But I put the grid there, so this grid is this one here. Now, or let me represent it by these bars, these things I have there. Round bars sitting on top of each other. And now, what will happen to this flow is that each of these rods will produce a little wake behind them. So that's one rod, another rod, another rod, another rod, like that. Okay? After a while, these wakes grow, and the turbulence sort of merges from each of these wakes, and now it is no longer distinguishable as separate wakes, but as a totally different flow which has merged together. And here, clearly, after they are all merged together, there is a translational invariance in this direction, so you can move up and down and you will have the same properties. It also turns out that it is, if you don't go too far, it's also homogeneous roughly in this direction. Although things will decay with distance a little bit, but the decay rate is so small that in fact it doesn't matter that much. So in fact, this is a very good approximation to this homogeneous turbulence. So there are a number of ways in which you can create such homogeneous turbulence, and therefore it is of some interest itself. More importantly, perhaps, is that if you look at this flow of one cylinder and let's say nothing else exists, and this kind of thing happens everywhere. This might be an aircraft, it might be a hill, anything you like. And clearly, turbulence is not going to be homogeneous at the edges because it will vary if you go up and down. But there is a certain region far enough from the boundaries where things are roughly homogeneous. So you might sort of think that there are regions in the flow, any flow, which may have, or which you might expect a priori to be roughly homogeneous, but you have to verify for yourself that it is so. It's not obvious that it would be so. Usual recipe is that far away from boundaries, far away from solid or otherwise boundaries, you would think that there are regions where homogeneity applies roughly. So for that reason, it's not unreasonable to look at a strictly homogeneous flow. And what happens here will have a lot to tell us about general dynamics of turbulence. And for the problem on hand, or the box problem, which is, I think, a good thing for you to keep in mind. So I have this box like that. So, and I have fluid inside, and I sort of shake the box in some low modes, not very fast, but slowly. So that's a forcing, you might call. And what happens is, if I keep shaking it, the flow here will be constantly in agitation. So it'll maintain itself statistically forever in a steady state. But suppose I shake the box and then leave it on this desk, then you can imagine that the fluctuations I created by shaking the box will sort of die away by viscosity, okay? So let's look at to simplify matters, let's simply look at the case of decay. So I shake the box and put it there, and turbulence decays. So you might say, what's the big deal about this? So everything else is zero. You see, I have the production zero, this transport term zero. I have just a, this is zero. I have rate of change of energy equals dissipation. What's the big deal, you might ask, right? I mean, it's such a trivial thing and you don't know how to solve that, you might ask. And the answer is, yes, we don't. And why don't we know? Let me say why it is sort of non-trivial. So let's make some order of magnitude estimates first, before we get too far. Excuse me, nonsense here. So let's say I have a RMS velocity of the order of 10 centimeters per second by shaking this box. Somehow I have made it like that. And then I have, let's say, so 10 centimeter per second is the velocity. And let's say this is 1 meter for the heck of it, 1 meter cube. You might say the velocity gradient, du dx, would be of the order 10 centimeters or 100 centimeters per second. Excuse me, I got it all wrong, right? Centimeter per second, yeah. So it's 1/10 per second. So I'm just making this very naive estimate, which I'm going to show is wrong in a minute. So this is a velocity, typical velocity and typical length scale here. And so I would have, therefore, if I write dE dt equals dissipation, the minus sign, as I did yesterday, because P turns out to be 0, see what happens here. I want to get an estimate for the energy here, which is 100 centimeters squared per second, and the dissipation will be nu is 0.15, assuming that to be air. I have this, whatever units it turns out. Now I want to calculate a time for decay of turbulence. Time for decay of turbulence is I have that much energy and I'm depleting it every second by that much. So I divide the total energy by however much I'm depleting every second, I get the number of seconds, right? So therefore the time would be is u squared over epsilon, that is, or d here, let's say, okay? And this is 100 here and whatever I have here, which is some number, this quantity here. And if I do that, I get something like 6 times 10 power 5 seconds. And when I was still asleep, I calculated that it is something like 10 days, so something like that. Now, that of course is nonsense, right? I mean, you obviously know that if you have a box that you shook and somehow put it on the desk, the air, it's, nothing else, nothing fancy there, you would expect it to die down in a matter of few minutes, not few days. So the reason for that is my estimate for this gradient is wrong. The fluctuations are not really varying like that. They are all over like that. There are little shear layers everywhere. So there are little gradients everywhere, and they actually dominate the estimate for the gradient that I should take there. And if I do the right thing, then I'll get the right answer, which is a few minutes or something like that. So somehow, what's happened here is that I have not shook the box, or shaken the box at these wavelengths or frequencies. I'm only shaking it very gently. Nevertheless, the flow itself, somehow by virtue of its own dynamics, creates internal shear layers into now small fluctuations in small scales. And so, schematically, if I look at the spectrum, so this is, let's say, for simplicity, let's say frequency, or I might put wave number here, but frequency, and I put in energy here. So when I'm forcing, I'm really forcing like that. So forcing at very low modes, low frequency, and somehow the flow creates fluctuations of all sorts, especially some large scale, large magnitude of fluctuations in high frequency. So somehow I have been able to, or the flow has been able to transport energy that I put in at low frequencies into high frequencies. This transfer of energy from low modes to high modes is happening, and that's part of the dynamics of turbulence. And that's what I would be able to study if I can understand what the problem is like. Okay? So that's an important generic problem in turbulence. That is, you create turbulence at low frequencies or low large scales, and then it will somehow or the other get converted to small scales where the gradients are very large, and therefore they can diminish the energy very much more efficiently. And therefore, I'll have a much larger estimate for this, a smaller estimate for t. How does this transfer from here to there? What really happens? Of course, all of this is happening because of nonlinearity. Nonlinearity is the one that will allow different modes to interact. And you might imagine that the energy somehow from here, it goes here directly. That is, somehow you put it in there, and suddenly flow becomes small scale in its manifestation. On the other hand, it could do like this. This energy is transferred to next level of frequencies. So it might fill in this part, and then it goes there, then it goes there, and then it goes there like that. Both of them are possible, right? So somehow, but something has to happen like this. So this is known as the direct transfer of energy. Direct because it's going from low to high without any intermediaries. And this one would be called energy cascade. Energy goes from one scale to neighboring scale, and neighboring scale to next neighboring scale, etc. This, of course, these two are very different scenarios, and the physical understanding of each flow of turbulence you might have depends on which of these is actually happening. And so we will see. We'll see what we know about this. This transfer of energy is the main problem that we would like to understand by doing the turbulence of the homogeneous flow. As I was saying earlier, the manifestation, an important manifestation of this energy transfer is that the gradients become sharper and therefore dissipate a lot more energy than you can imagine by other means. Now it turns out that the dissipation term has, if you look at this here, has the form nu times the square of the gradient of fluctuations. It's like that, right? So it's ui prime u x1 squared. I omit I and that sort of thing for now. So the larger the gradients, you might think, larger the dissipation. Vice versa, you might think that larger the viscosity, larger the dissipation, right? So if I did a turbulent flow in water and a turbulent flow in air, same flow, same Reynolds number, etc., and because the viscosity in water is 5 to 10 times more than that of much more, 10 times, let's say, more, then you might get kinematic viscosity. Kinematic viscosity of air is 0.15 centimeter squared per second. This is air, this is water, 0.01 centimeter squared per second. So something like that. I probably said the opposite way. So you might think that the dissipation in one case will be larger than the dissipation there, but one of the fascinating things about turbulence is it does not. So if I plotted as a function of, let's say, 1 over nu, I'll see why it's 1 over nu in a minute, and this is the energy dissipation rate in some fashion normalized and all that, then you would have thought, or I would have thought, that when larger the nu, that means smaller the 1 over nu, the energy dissipation would go up, but actually it would stay like that. Now, I have to make this more precise because I have to plot non-dimensional numbers which do not depend on the flow, etc. But now what is the implication of that? The implication of this is that smaller the viscosity, the flow adjusts itself so the gradients become larger in order for you to get the same product. You will of course know that such things happen in singular perturbation all over the place, where even though you have a small parameter sitting in front of some other gradient, then the flow adjusts itself so that the product of the two terms is of the order unity. So now you have a case where as the viscosity goes down to 0, these gradients become larger and larger and larger. In fact, viscosity here is in Reynolds number sitting in the bottom just as here. So I usually prefer to think of Reynolds number going up rather than viscosity going down. So the question is, of course, when viscosity is 0, exactly 0, what happens? Then you have Euler equations which doesn't have any dissipation. You might say that their singularities are Euler and that will somehow take care of the dissipation, but leave out singularities for now because no one knows. Therefore, the general idea is that the limit of nu going to 0 is not the same as nu equal to 0. This is what you know in boundary layers, etc. So even small amount of viscosity is necessary for you to have dissipation. It does not matter what its magnitude. The flow is clever enough to adjust itself, so it gives you the same dissipation rate. Now, nobody knows how to prove it theoretically, but empirically this is known. It's known. I can give you references to some papers, but in all of them, the behavior is sort of like that, is a little bit like that, coming down, and for high enough Reynolds numbers, it is independent of viscosity, and people who are very clever want to call it zeroth law of turbulence. Okay, but basically it is the so-called dissipative anomaly. Anomaly is that when the viscosity is 0, viscosity goes to 0, the dissipation does not go to 0 but remains finite. Okay, so we'll leave here, and when we come back, we will talk about the homogeneous turbulence proper.